Okay, welcome to lecture 12 from engineering metallurgy, phase diagram part 4. In the last class, we have studied the type 1 phase diagram, in which we studied how materials are slowly cooled and evolution of various structures inside the material, depending on the cooling in the single phase, two phase regions. And we also studied how to determine the chemical composition of phases and also the relative amount of these phases. And today we are going to talk about, in the last class it was type 2 diagram. So today it's going to be type 3. The basic of type 3 diagram is that two metals completely soluble in the liquid state, but only partly soluble in the solid state. In the last lecture it was about insoluble in the solid state. The two metals were completely insoluble in the solid state. But today, the two metals will be completely soluble in the liquid state and partly soluble in the solid state. So this is one of the representative diagram for type 3, in which if we look closely in this diagram, that we'll be able to see that there is a single phase region, that is the liquid at very high temperature. It also behaves similarly with the type 2 diagram, like when metal B is mixed with metal A, then melting point temperature actually drops and it meets at a point which is called Eutectic point, and also same occurs for element B, in which case if element A is added to element B, then the melting point temperature drops, and this drop meets to a point where the composition at a certain composition, and that composition is called the eutectic composition, and the temperature at which the eutectic mixture melts down or gets solidified, which is a constant temperature, and that is called eutectic temperature. And only deviation from the type 2 diagram is that in the case of type 2 diagram, we have seen that the solidus line actually intersects with the vertical line. That means 100% A and 100% B, it intersected. That means once the material gets solidified, the solid will contain only either material A or only either material B. That is like 100% A or 100% B. But in this case, this line TA, T4, T5, and F, this line, and on the other side TB and G, these two lines actually represents the solubility of, in this case, the solubility of B in A. This line actually indicates the solubility of B in A, and this line indicates the solubility of A in B. That means according to this line, how much A will be, how much B will be present in the solid, we can determine that using this line. And it also depends on the temperature. When the temperature drops, then the solubility increases up to this point. Solubility of B in A increases up to this point, and after that, in the solid state, the solubility actually decreases. When the temperature drops more in the solid state, then the solubility of B in A actually decreases, and that is indicated by this line. We'll actually explore this, like when we study L1, then we'll explore that how does it occur, how the changes occurs in the microstructure or in the crystal. Same will occur. The same thing will happen in the case of this region. And in here, we will actually indicate the solid that is formed as alpha. And so alpha will contain more A and less amount of B. And beta, in the case of beta will contain more B, and A will be soluble in B. Okay, that's how we define is the solid phase. When the when solidification starts, then there will be the mixture of solid and liquid, which is that's why this region is a two-phase region where there will be liquid and alpha solid solution. And in the case of in the other side, there will be solid of beta and liquid. This is the these two regions are the two-phase region, and also the solid in the solid state will be the two-phase region like alpha and beta. It will be the two-phase region, but this region in here, this region actually, this region is a single-phase region. Even alpha contains element B, you can treat it as a single phase because those crystals will be separated, will be a different appearance in the microstructure compared to these elements. So this is a different phase. Okay, and also beta is a different phase. So alpha and beta are different phases. When we actually introduce the definition of phase, we have said that if we look at the microstructure and if we see the different reflection, that means different color that appears in the microstructure will be treated as a phase, not in the molecular state or atomic scale. Okay, so we are not considering the atomic scale. So this will be alpha. Alpha will be one single phase, and beta will be another single phase. And this region will have two phases, like alpha and beta. The mixture of alpha and beta. Okay, any question in here?
Sir, এখানে alpha region আর beta region টা কি partly soluble নাকি insoluble?
Yes, partly soluble. That's what this alpha region and beta region is all about.
Sir,
okay.
স্যার তাহলে এটা কি মানে সলিউবল হবে এর ভিতরে আর ইউটেকটিক লাইনের ভিতরে ইনসলিউবল?
Yes, you are right in a sense, but the clarification is that in the case of alpha, it is a single phase, and when in the region of the eutectic region, eutectic mixture region, there will be two phase, like either alpha with eutectic mixture and beta with eutectic mixture. That's the two phase. Okay, and also if you look more closely, then in the eutectic mixture, it is not the mixture of element A and element B. It will be a mixture of alpha and beta. Okay, the eutectic mixture is also a mixture of alpha plus beta. So eventually, if we look at very closely in this region, then we'll see only two phases of alpha and beta. Okay, so when you see the microstructures, then it will be more clear. Okay.
Yes, sir.
All right. Any other question?
Sir, alpha or beta টা যদি একটু বলতেন স্যার, নেট প্রবলেম জন্য বুঝতে পারিনি।
Alpha is basically when the metal starts to solidify, it produces the crystals, and that crystals will be in the case of type 2 diagram, we have seen that the crystals are completely 100% crystals were 100% metal A. But in this case, since in the solid state, metal B can be into the matrix of metal A, so it will not be 100% A. The solid that is produced will be mixture of A and B. There will be like more A and less amount of B. That means B will be soluble in A, in the solid state. Okay, that's why the solid that is produced in here will contain B in it. Okay, that is alpha. And in the case of beta, the B will be more and A will be less. Okay, that is beta. Did you get it?
Yes, sir.
All right. So let's move on. Okay, let's study the equilibrium cooling of alloys. Let's say first, if you consider the alloy 1, in this case, when the temperature is at very high temperature, that means at T0 or higher than T1, then it will be liquid. And in the liquid state, as we know, the two metals are completely soluble. So it will be a single phase with metal A and metal B staying together. Okay. When the temperature starts to drop, in the case of alloy 1, this is an elaborated, that means expanded image. And if we look at the cooling curve, then we can, using the phase diagram, we can also draw the cooling curves. Okay, how to draw that? At a high temperature, it is completely liquid at this temperature. And when temperature comes to T1, then solidification starts. When the solidification starts, slope of this curve actually changes in here. So solidification starts at this point and solidification ends at this point, because this is the solidus line. Below this line, the material is completely solid. Okay, and then once solidification is complete, then it goes to the room temperature, and there is no eutectic in this case. Okay, and to be more clear in here, this is the combination of type 1 and type 2 diagram. Okay, in the case of type 1 diagram, we have seen that when the alloys solidifies, then the metal A and B are completely soluble up to this point. The alloys that in this region, from this line to the left side, all the alloys will show a phase diagram. This diagram is completely similar to type 1 diagram. That means metal B is completely soluble in metal A. And from this point to this point, from this composition to that composition, in this region, this actually behaves like type 2 diagram. Okay, type 2 diagram, and this one is type 1 diagram. And similarly, from this composition to this composition, this is actually type 1 diagram. Okay, so type 3 diagram is basically the combination of type 2 and type 1. Okay, now let's come to the solidification process. It will be similar to the type 1 diagram. Okay, at high temperature, there will be liquid solution which will have like 5% B, because this alloy is actually 5% B. This alloy is actually 5% B. So the liquid will have 5% B and 95% A. When the temperature drops and reaches a temperature T1, the material starts to solidify. And once the solidification starts, at a temperature below this line, like if you consider this temperature, because at close to this line, it is very difficult to explain. So if we go to further below, that means the temperature is in here. In this case, we will see that there will be certain amount of solid. How do we know how much solid is produced, or what will be the composition of that solid? In that case, we need to draw the tie line, right? And to draw the tie line will be connected with a horizontal line, which is a connecting line between solidus line and liquidus line. So this is the liquidus line in here, and this is the solidus line in here. So the tie line will be in between them at this temperature. Okay, so at this temperature, once we draw the tie line, this is the two-phase region which contains liquid and alpha. Alpha is the solid. Okay, so there is liquid and there is solid. So how much solid is present in here, we can determine that using the tie line. So in that case, we have to consider which distance, this one or this one. Can anyone say? To find out how much solid is in there at that temperature.
লিকুইড পর্যন্ত যেতে লিকুইডাস লাইনে যাইতে হবে স্যার।
Yes, definitely. So to find out the percentage of solid, we have to consider this length. So to find out the percentage of solid, we have to consider this length, and to find out the percentage of liquid, we have to consider this line according to the lever rule. And to find out the composition, what is the composition of the solid? To find out the composition of the solid, we have to go to the solidus line, and then you can read the composition. It is like 2% B. So the solid that is produced, that means solid crystals that is produced at this temperature, will have 2% B and 98% A. That is more A and very small amount of B. And B is soluble in A. That means in the solid crystals of A, there will be B also. And this is the alpha. Okay. And the liquid composition, we can read the liquid composition from liquidus line, and from this point, so the liquid composition will be 20B and 80A. Okay, any confusion in here? It is similar to type 1 diagram. All right. So when the temperature drops more, then more and more solid are produced. And when the temperature drops below this line, then there will be 100% solid. And 100% solid, it is not like the composition will be same. When from this point to the room temperature, the composition of the solid will be same. That means the solid will have 5% B and 95% A. Okay, 5% B and 95% A. Because this is the alloy of 95% A, 5% B. In the liquid state, it was completely soluble, and in the solid state, it is completely soluble. So this curve is basically this region up to this point is basically a type 1 diagram. Okay, any question? All right. So let's move to next one. Alloy 2. We'll move to alloy 4 at the end because it's a bit complicated. Before we move to alloy 4, then we have to finish alloy 2. What happens in the case of alloy 2? In the case of alloy 2, as you know, it is the composition 70% B and 30% A. This is the eutectic point. So this composition is an eutectic composition, and the cooling curve in this case will have a horizontal line in the cooling curve. And this is the start of solidification, and this is the end of solidification. And what will happen in this case, in the case of alloy 2, is that instead of solidifying metal A and metal B, it actually solidifies as alpha and beta. Okay, this material actually solidifies as alpha and beta. And what will be the composition of alpha and what will be the composition of beta? That is the challenge here. Okay. In this case, the reaction that occurs is the eutectic reaction. In this case, the liquid actually solidifies at a constant temperature to solid 1 and solid 2. And solid 1 is alpha and solid 2 is beta. Now, the composition. What is the composition of alpha and what is the composition of beta? To find that out, the composition of alpha and beta, from this eutectic temperature point, if we move to the left, it intersects in the solid region in here. And that also intersects in the solid region in here at this line. Okay. So this point will give you the composition, since this is close to beta. So this is the two-phase region which contains alpha and beta. So this line represents the beta and this line represents alpha. Okay, so to read the composition of alpha and composition of beta, we have to move to the left and right. In the case of, if we move to the left, in here the composition is 20% B, so alpha will have a composition of 20% B, and beta that is produced in this region will have a composition of almost 92%, let's say 92% B, and rest of it is A. So in the case of eutectic reaction, when solid 1 and solid 2 is formed, that is alpha and beta is formed, and alpha will have a composition of that can be read from the alpha line, that is solvers line of alpha, and the solvers line of beta. And when the temperature drops from eutectic temperature to the room temperature, actually the composition changes. Okay, percentage of alpha and beta will be the same. It will be like in this case the 100% eutectic mixture. It is a two-phase region, alpha and beta. It will be the same, but the problem is that the composition of alpha and chemical composition of alpha and chemical composition of beta changes when the temperature drops. Let's say if the temperature drops to this temperature, at this temperature. Then if we read the composition of alpha will be like very close to 95%. Sorry, composition of beta will be very close to 95%, and composition of A will be very close to let's say 12% B. Okay, so even at the when the solid is formed, because of the diffusion, the composition of alpha and beta also changes. Now the question, another question is like how much alpha is present in there and how much beta is present in there. We have known, we have found out that how much what is the chemical composition of alpha and what is the chemical composition of beta. But if we also need to find out how much percentage of alpha is there and how much percentage of beta is there. And how do we do that? We have to do that at a certain temperature. If we consider that eutectic point temperature, what is the percentage of solid? If we want to find out the percentage of alpha will be equals to the total length from this point to that point. Okay, that means Fg will be the total length that will stay below in here. And to find out the composition of alpha, percentage of alpha, we have to again use the lever rule. So this will act as Fg will act as a tie line. So the length from this point to that point will give us the percentage amount, that is Eg. Eg will give us the percentage of alpha present in the eutectic mixture, and from F to E, Fe, this length will give us the percentage of beta will be found from Fg and Ef. That's how we determine in the case of eutectic mixture of type 3 diagram, to find out the percentage of alpha and percentage of beta, we can use these tie lines. But when the temperature drops, okay, when the temperature drops, then tie line will also drop. Okay, when the temperature drops, then let's say if it is at this temperature, okay, then the tie line will drop and chemical composition changes, as well as the percentage of alpha and beta will also change. How can we determine that? We have to find out this length to find out the percentage of alpha, and we have to find out this length to find out the percentage of beta. Okay, it is similar. Okay, any question in the case of alloy 2? No question?
স্যার এখানে লাস্টের কম্পোজিশনের মানে আলফা বিটার পার্সেন্টেজটা কিভাবে আবার একটু
Okay, so we know that alloy 2 solidifies at a constant temperature, and upon solidification, the crystals that are formed, let's say this is one of the crystal, it will have alpha and beta side by side. Okay, and we have to find out the alpha that is present. Let's say if I draw it more elaborately, let's say this red region is indicating alpha, and the white region is indicating beta. So they will be solidified side by side, similar to the eutectic mixture that we have seen in the case of type 2 diagram. Okay, in the case of type 2 diagram, we have seen that it will be like metal A and metal B, but in the case of type 3 diagram, it will be alpha and beta solidified side by side. Okay, now first we have determined the chemical composition of alpha just after solidification. That means at a temperature TE, at eutectic temperature, we have found that alpha will have a composition of from this point like 20% B, 20% B, and the beta will have a composition of if we go move to this point, it will be like 92% B 92% B. So far, did you understand?
Yes, sir.
Okay. Now, in the microstructure, that means in the solid, how much alpha is present? What is the percentage of alpha and what is the percentage of beta? To find that out, we have to consider the total a tie line that intersects from solidus line to liquidus line. In the case of two-phase region, solid and liquid, and in this case, the two-phase region is about alpha solvus line. This is alpha solvus line, and this is solvus line for beta. Okay, so in this case, it is also two-phase region, and the phases are alpha and beta. So the tie line will be in between these two solvus line. Okay, so in the case of at a temperature TE, eutectic temperature, the tie line will be from the point F to point G. And to find out the percentage of alpha, we have to apply the lever rule. So total length will be FG, and the length from E to G, from this E point to G point, is will give us the E G will give us the percentage of alpha present. Okay, did you understand this?
Yes, sir.
And so how to determine the percentage of beta?
Sir, same process. Just
Same process, or you can just 1 minus alpha. You can do this too, or you can use like F to EF divided by FG. Now, when the temperature drops, since the composition changes, the amount of alpha and beta will also change. Okay, and to do that, if you want to, for example, find out the percentage of alpha and percentage of beta at room temperature, and this indicates the room temperature, this line actually indicates the room temperature from H to J. So in this case, to find out alpha, how can we find out alpha? So the tie line total length is Hj. This is the total length of the tie line.
Yes.
And to find out the percentage of alpha, we have to consider length K to J. So from K to J, this will give us the percentage of alpha in the room at room temperature. Okay.
Yes, sir.
All right. So let's move to alloy 3.
ইজি নিচ্ছে কি কারণে? আমরা তো মানে ওই সাইডটা তো বিটা রিজিয়ন না, তাহলে তো আমাদের স্যার মানে সামনের এফ ই নেওয়া উচিত না, আমরা ইজি নিচ্ছি কি কারণে?
It is the lever rule. The rule 2 actually says that if you have a tie line between two different phases, let's say this is phase 1, phase 2, and this is phase 1. For a certain alloy, if you want to find out the chemical composition of phase 1, then you read the chemical composition from here. If you want to find out the chemical, according to the rule 1, if you want to find out the chemical composition of phase 2, then you find out the chemical composition of from phase 2 line. But when you want to find out the percentage of P1, then the rule is rule 2. In the case of rule 2 says that it is a lever rule. That means if you want to find out the percentage of P1, then you have to consider this length. Okay.
Yes,
if
sir,
you want to find out the percentage of P2, then you have to consider this length. Okay.
জি স্যার, বুঝতে পারছি। জি স্যার।
All right. So next, move to the alloy 3. So in the case of alloy 3, as I said previously, it is completely similar to the type 2 diagram. Okay. As I said, from this point, the alloys from 20% to 70%, this will act as the phase diagram that is produced in here. It will be similar to type 2 diagram. Okay, so let's see how the microstructural evolution occurs in the case of alloy 3. At a very high temperature, the liquid solution will have like 40% B, since the alloy 3 is 40% B. So it is completely soluble in A. So it will show a completely single phase, and that will have like 40% B and 60% A. And it will be a uniform distribution. When the temperature drops below this liquidus line at this temperature, the solidification actually started. Certain amount of solid has been produced, and that certain amount of solid that has been produced, if we want to find out the chemical composition of the solid that has been produced at this temperature, then we have to draw the tie line between the phases. So this will have the liquid phase, and this is the solid phase. So the tie line will be in between them. This is the tie line. Once you draw the tie line, then if we want to find out the chemical composition of alpha, that means the solid that has been produced, then we have to read the composition from this point. So the composition from this point, if we read it, then it is like 10% B. So the crystals that has been produced will have a composition of 10% B. That is alpha solid solution. Okay. And if we want to read the composition of the remaining liquid, then we have to move to this point. So this point will give us the chemical composition of 50% B. So the liquid that is present in here will have 50% B. Will have a chemical composition of 50% B. So now, if you want to find out how much alpha solid solution is produced, then to find out the percentage, we have to, let's say we denote it like X, this is Y, and this is O. Okay. So to find out the chemical composition, percentage of alpha solid solution, then we have to consider the total length. Total length is X and Y. Okay. And the solid percentage of solid will give us from this length up to the liquid phase. Okay. So this length is O, Y. Okay. So from this, we can find out the alpha solid solution percentage, and to find out the liquid solution percentage, we have to find out like X, Y will be the total length of the tie line, and XD will give us XO. Sorry, XO will XO will give us the percentage of liquid present at this temperature. Okay. Now, again, when the temperature drops, solidification continues, and the crystals will have the A and B both on it. So the solid amount of solid will increase up to at this point. When you go to the eutectic temperature line, then there will be some liquid and some solid. Solid percentage will be more, and also solid will have more B in it. Okay. Because if we read the composition before solidification at the eutectic temperature, then the composition of solid will have like solid chemical composition will be like 20% B. Solid will have chemical composition of 20% B, and liquid will have composition of eutectic composition. That is 70% B. 70% B is the eutectic composition. So as we see from when the temperature drops from T3 to TE, the solid percentage increases. This is definite. Okay, and at the same time, the percentage of B in the solid, that means in the chemical composition of solid, the amount of B also increases. And how can we say that? According to this line. This line actually defines like how much B can be present at a certain temperature. Let's say at this temperature, the maximum amount of B that can be present in the solid is 10%. But when the temperature reaches at TE, the maximum amount of B that can be present in the solid is 20% B. And that is indicated by this line. If you draw another line in here, then you'll see that the chemical percentage of B is increasing, because this line is the chemical composition is increasing according to this line. Okay, so once the temperature drops from a certain from the liquidus line to the eutectic temperature line, amount of solid, that means amount of alpha solid solution increases. At the same time, the amount of B in the solid solution will also increase. Okay. And when the temperature TE is reached, the chemical composition of the liquid is 70% B. And 70% B is a eutectic composition. Okay. Since 70% B is an eutectic composition and the temperature is also at TE, that means at eutectic temperature. So the solidification in this region, the rest of the liquid that is present in here will solidify according to the eutectic reaction at a constant temperature. That is indicated in the, if you look at this cooling curve. At temperature TE, solidification starts and alpha starts to produce. Alpha production continues up to TE. At TE, alpha production is complete. And then the eutectic mixture will start to produce. And at this temperature TE, rest of the liquid of 70% B will start to solidify at a constant temperature and solidification will end. And how does that solidification occur? It's like production of alpha, and then on both sides there will be beta. Okay, and this will be a uniform mixture of alpha, and beta. Okay, so after solidification, we'll see that the alpha solid solution that has been produced before eutectic reaction will remain the same. It will have the same chemical composition and the percentage amount will also be same, but the rest of the liquid that was before eutectic reaction has converted to eutectic mixture with the same chemical composition, 70% B, but it will have alpha and beta together and separately. Alpha and beta will not be mixed together. They will stay separate but side by side. And that after that, when the temperature drops, then the chemical composition also changes, because at this point, temperature TE, the maximum amount of B that can be present in alpha is 20%. But when the temperature drops to this temperature, the maximum amount of B that can be present in alpha has been reduced. So alpha will release some B, some atoms of B. Alpha, when the temperature drops, alpha from alpha of 20% B, some of the B atom will be diffused away from alpha solid solution, and they will move to the beta solid solution. Okay, and the chemical composition will also change. So in this case, when the temperature drops, then there will be the alpha solid solution will have less amount of B, but the percentage will also change. Okay, so the total, if you want to find out the total percentage, then you have to draw the tie line in this region and then find out how much eutectic mixture is there and how much alpha is present in there and how much beta is present in there. But in larger scale, if you look at the microstructure, you'll be able to see the grains of alpha solid solution with eutectic mixture of alpha and beta solid solutions. Okay, any question?
স্যার তার মানে এখানে ইউটেকটিক টেম্পারেচারের আগ পর্যন্ত টাইপ 2 টাইপের আর তারপরে ডিফারেন্ট।
Yes, in the solid state it will be different, and the composition of alpha and beta will change according to the solver size. Okay.
Yes, sir.
Okay, anyone else? Okay, no. Then I want to make some more comments in here. First is that if we have an alloy in this region, in here, that will have maximum amount of solid. That means maximum amount of alpha solid solution and small amount of mixture of alpha and beta. Once we move in this direction, then alpha solid solution will start to decrease. The grains of alpha will reduce and the grains of eutectic mixture will increase up to this point. At this point, there will be 100% eutectic mixture. Did you understand this?
Yes,
No,
sir.
sir.
No. Okay. So to clarify it, if we have an alloy in here at this region, at this temperature, if you consider this temperature, okay, at this temperature, how much solid is present? That can be represented from this point to that point, right? So there is huge amount of alpha solid solution present before solidification, complete solidification. Okay, and very small amount of liquid is present, and that liquid upon solidification will be converted to the eutectic mixture. So in here we'll see a microstructure will have mostly the grains of alpha and very small amount of grains of eutectic mixture. But if we consider an alloy in this in here, that will have very small amount of solid, that means very small amount of alpha solid solution and a large amount of eutectic mixture, and at the eutectic temperature, eutectic mixture, it will have 100%, the microstructure will have 100% eutectic mixture. That means that if we increase the percentage of B in the alloy, then more and more eutectic mixture is produced. Did you understand now?
Yes, sir.
Okay. So before we move to L4, let's come back in here. So as I said, from this point, if we move to the right, the amount of eutectic mixture increases as we move to the right. And at eutectic temperature, the eutectic mixture is 100%. Beyond this, when we move further, that means when we increase the composition of B further, then along with eutectic mixture, there will be crystals of beta. Okay, that means from this point to the right, as we move to the right up to point G, so there will be crystals of beta will increase. Okay, so if we consider an alloy in here, then it will have small amount of beta and large amount of eutectic mixture. If you consider an alloy in here, that will have large amount of beta and a small amount of eutectic mixture. Okay.
Yes, sir.
And if we move further from this point, like in this region, if we consider an alloy in this region, so at this temperature, it will be completely beta, 100% beta. Okay. And if we go less than, if we add like less than 20% B in A, so it will have, at this temperature, it will have 100% alpha. So crystal structure will have 100% alpha. Okay. That means on the left side, crystals will be 100% alpha, and after this point, eutectic mixture will start to produce, and its eutectic mixture will increase and become 100% in here, and beyond that, the eutectic mixture will start to reduce and beta will start to increase. And at this point, after this point, the beta will be 100% at this temperature. Okay.
Yes, sir.
Okay, now let's come to alloy 4. So in the case of alloy 4, it is same up to this point. At a high temperature, it is completely liquid and uniform mixture of 15% B. Alloy 4 is about 15% B. Okay, it will have 50% B and 85% A. And so this is the uniform chemical composition will be found in here, and also the single phase will be found. And this from temperature T2 to T5, it will behave like type 1 diagram. So there will be solids increasing as the temperature decrease. With the decrease of temperature, amount of solid will increase. At the same time, the chemical composition of alpha will indicate that the percentage of B is also increasing. At this temperature, at T5, there will be 100% alpha will be produced with 15% B. Okay, 100% alpha will be produced. That means complete solidification is complete at this point. And then when it goes to this region, this is 100% alpha. Okay, in this region, it is 100% alpha. And when the temperature drops, it will have like 100% alpha. Okay, but when it reaches the solvers line in here, the problem starts to occur. That means when the temperature drops and it crosses the solvers line, then there is a change in chemical composition that occurs. That means in the solid state, even after solidification is complete, if you pull it slowly, then what will happen is that some of the alpha solution will release the B. The alpha solid solution have 15% B in this region at M. But when it crosses N, then some of the B from alpha solid solution will be released. And that that element B will be combined with some of the solids, with some of the atoms of A. And they will produce beta solid solution at the grain, mostly at the grain boundaries. Okay, mostly at the grain boundaries, there will be, when the solvers line is crossed, there will be solid solution of beta will, of B will also be present there. Okay, so that means it is like if I want to give an example, like you have a group of five people. Okay, there is a 2 group. There are 5 members in each group. Okay, 5 different members, and if you from the groups, if some of the people leave from a group and they try to form another group with A, maximum amount of A that they can take on them. So the atom B that has been released from alpha solid solution, they produce their own group by taking some of the A with them, and that is the beta solid solution. And the beta solid solution is produced once the solvers line is crossed. Okay, any question? Did you understand the phenomena in here from N to H? What happens in the case of when temperature drop from N to H?
Yes, sir.
Anyone else? It is not like Samira is attending the class. All of you are attending the class, so please, you have to respond.
Yes, sir.
Okay, 2 is enough, I guess. Okay, that's it about type 3 diagram. This is how the type 3 diagram works. And if we want to see the real life example of type 3 diagram, so this is one of the example which contains lead and antimony diagram. Element A is lead and element B is antimony. That means 100% lead is in here and 100% antimony is in here. Okay, so it has like alpha in this region and the beta is in this region, but at room temperature there is no alpha or beta. Okay, it is like at room temperature. When it comes to the room temperature, then they are like 100% A, so 100% lead and 100% beta. Okay, In this case, this is the alpha region, and this is the liquid and alpha region, two-phase region. This is also the two-phase region, and this is beta region. Okay, and when if we look at the microstructure for alloy 1, that means alloy 1 will be in here. In the case of alloy 1, 6.5% antimony. Okay, in the case of 6.5% antimony, if we look at the crystals, crystal structure, then we'll see like there will be the crystals of what crystal should be in there? Crystals that have been produced here will be alpha. That means it will have more lead and 6.5% antimony in this region. And rest of the liquid that has been present before this eutectic temperature line will be converted to eutectic mixture. Okay, and these regions will actually is actually indicating the mixture of alpha and beta, alpha plus beta. That is the eutectic mixture. And if you consider the alloy at 2, this is like 11.5% antimony. It is the eutectic mixture for eutectic point. So the composition is eutectic composition. So the microstructure will be the uniform mixture of antimony and lead. Okay. At the room temperature, it will be antimony and lead, but at a temperature just below the eutectic temperature, it will be the alpha and beta, mixture of alpha and beta. And if you go further, like at 3, alloy 3, in this case, the crystals that have been formed will be will consist of mostly the antimony crystals will be produced, and along with them there will be the mixture of antimony and lead, or alpha and beta. The mixtures will be a mixture of alpha and beta, and there will be some crystals of antimony. If we move further, like 80% antimony, most of the crystals will be antimony, and the very small amount of mixture of lead and antimony or alpha and beta will be present in the microstructure.
Sir,
Yes.
এখানে রুম টেম্পারেচারের নিচে সলভাস লাইনটা যেহেতু দেখা যাচ্ছে না, এখানে কি এই কারণে আলফা বিটা কমে যাবে?
Yes, that is the reason. Since the solvus line is intersecting with the 100% solid line, right, in this region, that means below the temperature 50 degree, there will not be any alpha. Alpha will release the atoms of antimony and become pure lead. Okay, so it depends on the this solvus line actually indicates how much antimony can be present in the matrix of lead, and this solvus line represents how much lead can be present in the matrix of antimony. Okay.
Yes, sir.
All right. Any other question? Okay. Let's move forward. This is another diagram, lead and tin. Okay. And another thing I should mention in here before we move further. Okay. Clear it out. Okay. So this is an hypothetical diagram. Always remember that we are considering element A and element B. Okay. The type 3 diagram, it's not necessary that it will always look like this. Just like the eutectic mixture, it's not like constant. For all the materials, it will be at 70% B. It's not like that. It can be anywhere. It can be 20% B. It can be 90% B, anywhere. And also these solvus lines, it will also change based on the material. Different material will show different type of solvus line. And it is also not necessary that both of the material will show the solubility. That means in another side, it may not have any beta produced in here. It can be like pure type 2 diagram. But in this region, there might be solubility. That means material B can be soluble in metal A, but metal A cannot be soluble in metal B. It might happen. So there can be in real examples, this is an idealized diagram. Okay, this diagram is very idealized. So there might be different variations as we have seen in the case of antimony and lead. If you look at the diagram of antimony and lead, in this diagram we see that the eutectic point is at 11.5%. And at room temperature, there is no solubility of antimony in lead. And also in the case of, but in the case of antimony, lead in antimony, there is a slight amount of solubility present. Okay, so it can be different. Like if you look at this diagram, lead and tin diagram, we'll see that you have a significant amount of tin can be in the matrix of lead, but in the matrix of tin at below temperature 300, there is no. It is not possible to hold the atoms of lead in the crystals of tin. Okay, so there might be different variations, but the basic is the same. Okay, did you get my point?
Yes, sir.
Yes, sir.
Okay, so in this case, do I need to explain this? Oh, yes, go ahead. Hello.
Yes, sir.
Okay, so in the case of like alloy 1, it is 70% tin and 61.9% tin. In the case of 61.9% tin, it is an eutectic mixture. So this is the microstructure will look like the eutectic mixture. In 70% tin, there will be crystals of tin. Okay, crystals of tin with the eutectic mixture. Okay, and in the case of 60% tin, less than the eutectic point. So the crystals here will be the crystals of lead with the mixture of lead and alpha and beta. That means tin. The alpha will have like lead in tin in lead. So it will be the mixture of tin and lead. And at 50%, there will be more crystals of lead. Okay, more crystals of lead. It's not actually lead. It is the more crystals of alpha, which contains both maximum amount of lead and small amount of tin. Okay, tin SB, right?
Yes.
Okay, so that's how the microstructural evolution occurs in the case of if you change the alloys. Okay, and to get the different property, for example, you have a 70% tin alloy like this alloy. Okay, so once you cool down slowly, that will have like the crystal, like uniform crystals of of tin with the mixture of lead and tin. Okay, but if you cool it from a certain temperature very quickly, then it will retain the structure. So less amount of tin crystal will be there. Okay, so you'll have a different property. So you can modify the properties. Okay, according to the by cooling it rapidly from various temperature. Okay, so for example, a good example could be like 10% tin. In the case of 10% tin at temperature 200 degree, this is 100% alpha, right?
Yes, sir.
Yes, sir.
But if you cool it very quickly from this temperature to the room temperature, okay, less than 100%, then you can have 100% alpha at room temperature by cooling it very rapidly. But if you cool it slowly, then you will not have 100% alpha, because once the solvers line is crossed, there will be beta present. Beta will come. So the mechanical property will be different. Okay. That's why we need the phase diagram to understand from a single alloy how many different properties we can obtain. All right.
Yes.
Okay, so the next we'll move to the type 4 diagram. It's a very simple diagram, so I would like to finish this one today. It is a congruent melting intermediate phase. It is a compound type alloy that is formed in the type 4 diagram. When one phase changes into another phase isothermally, that means at constant temperature and without any change in chemical composition, it is said to be congruent phase change or congruent transformation. That means when the phase change occurs, that means from one phase to another phase, that means from let's say, for example, from liquid to solid, a phase change occurs without the change in chemical composition, similar to the eutectic point, eutectic mixture. In this case, there is no change in chemical composition, just from phase change occurs. And those alloys are called congruent phase change. Those changes called for congruent phase change, and alloys are called congruent melting intermediate phase. Okay. And all pure metals solidify congruently. That means they do not change the chemical composition. And also the eutectic mixture don't. There's no chemical change. Okay. So in the case of compounds, also that same thing occurs. That means intermediate phases, because they are single phases that occur between terminal phases on a phase diagram. So if in a phase diagram, if you look at a phase diagram in here, like this is 100% A and this is 100% B, at certain proportion of A and B, the melting point completely changes. It shows a different melting point, just like the eutectic mixture. It shows a different melting point. But in the case of compound alloy, it might be the temperature, melting point temperature might increase. Okay, it might show a different melting point temperature. Okay, and that alloy actually solidifies at a constant temperature, and there is no chemical change occur during the transformation from liquid to solid. Okay, so in this case, the vertical line, this line indicates an intermediate alloy between A and B. Okay, since it is a compound, it is indicated as AMPN. So in the case of compound, you can indicate it like AMPN because it is constant. Okay, percentage of A and B is constant, and also M and N number of atoms in the compound. Okay, so the M and N indicates the number of atoms in the compound. And if the compound shows no solubility for either pure metal, okay, sometimes the compound may not show any solubility in metal A. Okay, and this compound may not also show the solubility in metal B. Sometimes it can. Okay, depending on that, the equilibrium diagram will be different. Okay, so in this case, what I've tried to show is that if the compound shows no solubility for either pure metal, that means it does not show any solubility in the metal A or metal B. Okay, so it will be the phase diagram will be like this. Okay, and if the pure metal shows some solubility for each other, okay, the equilibrium diagram will look like this. That means AMBN, the melting, the intermediate alloy, this alloy does not have any interaction with either A or B. That means A is not soluble in this compound. B is also not soluble in this compound. But B is soluble in A. That is indicated by the solvus line. And A is also soluble in B. That is indicated by the solvus line. Okay. And the phase diagram has been divided into two groups. Okay. One group indicating from 100% A to AMBN, and another is AMBN to B. So it is a separate two different diagram. So if we consider an alloy in this region, so it will be 100% alpha. If we consider an alloy in this region, it will be some alpha and some eutectic mixture, since this is an eutectic point. Okay, and what will happen in the case of eutectic mixture, it is not like alpha and beta. It will be alpha and this alloy and this intermediate alloy. So there is no interaction with the other side of the phase diagram. Okay, so if you consider an alloy in this region, it will be the 100% uniform mixture of alpha and AMBN. Okay, that means if we draw a crystal structure in this for this alloy, then we'll see some crystals of alpha, and rest will be the mixture of alpha and AMBN. And if we see the microstructure in this at this point, at this eutectic region, then it will be the uniform mixture of alpha and AMBN. And if we consider an alloy in here, then the microstructure will look like the crystals of AMBN, and the rest of it will be the crystal will be like AMBN, and the rest of the liquid will be transformed into the mixture of alpha plus AMBN. Okay, the mixture of alpha and AMBN. It is similar to type 3 diagram. The only difference is that there will be an intermediate alloy that is indicated by this vertical line. Okay, and on the other side, if we consider an alloy in here, then it will have the crystals of AMBN, and when this temperature T2 is crossed, then there will be crystals. The crystals that is formed in here will be AMBN, and the rest of the crystals after the Eutectic reaction, the rest of the crystals will be the mixture of AMBN and beta. And if you consider here, then it will be crystals of beta with the mixture of AMBN and beta. And if you consider a crystal here, then it will be 100% beta. So it is two different type 3 diagram will be produced in the case of concurrent melting intermediate phase or type 4 diagram. Okay, any question?
স্যার এখানে ইউটেকটিক মিক্সচারটা কি AMBN আর হয় আলফা না হয় বিটা?
Yes, there will be two types of eutectic mixture. One type will be the alpha and AMBN, and another type will be beta and AMBN.
ওকে স্যার। Yes sir.
So that's it for today, and in the next class we'll see type 4. We have already seen type 4, so it will be like type 5, 6 and 7. Okay, there will be three type diagrams we will study in the next lecture.